Awesome. All right. So I just tested out the recorded webinar from Monday, and it is showing my writing. So hopefully that'll stay. So the recorded ones on Mondays should now be working, I hope. But tonight we'll go through these examples from the week 3 material. The first thing we'll look at is algorithms and pseudocode, look at some properties of integers, use the Euclidean algorithm, and look at some mathematical induction problems. And then any other questions you guys have. So because there's not very many of you guys tonight, if there are things that I'm going over that you don't need me to go over, let me know. I don't want to waste your time. And if there's things that I don't talk about, please let me know. All right. So here's an example with pseudocode. You're asked in your homework to do two things. One is to create your own pseudocode, and one is to follow pseudocode. So here's an example of following it. And I just want to write down what these things mean. So step 1, what that's really saying is that x is equal to 0. So in terms of like code, think about in the x position, like somewhere in the computer they need to store what x is. In that spot, in that storage spot, there is a 0. And then step 2 says in the y storage position there's also a 0. Then it says while x is less than n, so here our n is 3 because that's given to us, that'll always be given. X right now is 0, so 0 is less than 3. That is true, so I'm going to do steps A and B. So this is saying this arrow, or backwards arrow, means assign that position, that storage spot. So in the X storage spot, we're going to take the previous value, which is 0, and add 1 to it. So now in our storage spot X, we're going to store a 1. In our Y storage spot, it's going to be the previous Y value, so 0, plus what's currently in our X storage spot. So the most recent X that we have is 1. So now in our Y storage spot, we have a 1. And then I'm in a loop right now, so this kind of A-B part is a loop, so I'm going to loop back up. And now I'm going to check again, is my x less than n? So my x is 1. It is less than 3. So I'm going to repeat these steps. So in my storage spot for x, it's the previous x value plus 1. So I get 2. And my y storage spot is my previous y, which is 1, plus my most recent x value, which is 2. So I get 3. And now I check again. Is my x is 2, is that less than 3? Yes. So I'm going to repeat those steps. So in my x storage spot, it's the previous x plus 1, which is 3. And my y value is my previous y plus my most recent x value, which is 3. So right now I have a 6 in my y storage spot. And now I check again. Is my x value, so my x is 3, is 3 less than 3? No, so I don't repeat the loop, and now I go to step 4. So step 4 says y, the storage place y, is now going to contain my most recent y value, which is 6, divided by 2. So 3. So the output would be a 3 value for my y. Are there questions on that pseudocode? Okay. So let's go to the next thing. Alright, so the GCD and the LCM, so GCD is greatest common divisor, LCM is least common multiple, so those are kind of what we'll look at next. And I want to find the GCD of two integers. So I have 45 and 33. And then, so finding the GCD is something you did in middle school, which I realize may have been a long time ago. But really the hard part is, how do you write it as s times 45 plus t times 33? So really it's a linear combination of those two things if you've had linear algebra. So first thing I want to do, so here's my larger value, so whichever one is larger, you start with that, and here's your smaller one. So 45 is 1 times 33 plus 12. So this is kind of the division algorithm. So in other words, how many times does 33 go into 45? It goes in one time, and the remainder is 12. And then I'm going to repeat this process over again using my 33 and 12. So 12 goes into 33 two times. So 2 times 12 is 24, and then plus 9 to get to 33. And repeat again. You're going to repeat until your remainder is 0. So 9 goes into 12 one time, remainder of 3. And then 3 goes into 9 three times, remainder is 0. So you stop when you hit a remainder of 0, and the remainder above the 0 is your GCD. So the biggest value that goes into both 45 and 33 is 3. So that's just finding the GCD. Now to write the GCD, or to write 3 as some number times 45 plus some number times 33, I'm going to rearrange all of these equations I have right here. I'm just going to do it on the next page. So this first one is just copying over what we just wrote. So 45 is 1 times 33 plus 12. I'm going to solve all three of these equations for the remainder. So I'm just going to put the 1 times 33 on the other side. Then we do the same thing when we solve for 9. So 9 is 33 minus 2 times 12. And then 3 is equal to 12 minus 1 times 9. So the big scheme of things, what we're going to do now, so we're trying to get 3 equal to this combination. So I'm going to kind of do a back substitution. So in for this 12, let me use a different color. In for this 12, sorry, that's not what I want to say. I want to replace the 9. In for this 9, those are the same, so I'm going to put in 33 minus 2 times 12 into that 9 spot. So let me stop talking and just show you. Alright, so this was 3 equals 12 minus 1 times 9. I'm going to replace that 9 with the 33. So take out the 9 and put in the 33 minus 2 times 12. And now I'm going to just do some algebra. I say just, but this is where it often gets confusing for people. So you have 12. I'm going to distribute my negative. I have minus 33 plus 2 times 12. Now I have 112 here. I have 2 12s here. So if I combine them, I get 3 12s minus 33. And then I'm going to replace the 12. So let's go back to the previous page. I have 12 is equal to 45 minus 1 times 33. So that's what I'm going to plug in. So this is 3 times 45 minus 1 times 33. And then I have a minus 33 from this piece. And now I'm going to rearrange again. So I'm going to distribute my 3. So I get 3 times 45 minus 3 times 33 minus 33. So I have 3 45s, and then I have negative 3 33s and another negative 1 33. So that's a minus 4 times 33. And this is what I was trying to get. This is my S times 45 plus T times 33. So I have done it. My S is 3 and the T is negative 4. Oh, you guys are awfully quiet. Is that okay? Any questions? Okay. You guys are just quiet tonight. So in terms of finding the LCM of the same two numbers, there are multiple ways to do it. The quickest way to do it is that the GCD of 45 and 33 times the LCM of 45 and 33 is equal to the product of 45 and 33. I don't know, I just wrote those backwards. So we know the GCD is 3. I'm trying to find the LCM, and then 33 times 45 is 1485. Just divide by 3 and you'll get your LCM. Okay, so then the next kind of is a modular arithmetic. So here we have an example with a mod 11 function. So really that just means, like they often call it clock arithmetic. So if our clock only went to 11 and then repeated itself again, that's kind of what's going on. So I'm going to write it as, like, so f of 39. 39 can be written as, something times 11 plus the remainder. So it's 3 times 11, that's 33, plus 6. So if we went, this means we'd go, if it was a clock to 11, we'd go around the clock 3 times, and then we'd get to 6 after that. So this is 6. In Wolfram Alpha, if you type 39 mod 11, it'll tell you 6. So just know that you can use Wolfram Alpha also to check yourself. For the f of 175, so 175 is something times 11 plus some remainder. I think it's 15. I forgot that number. The remainder is 10, which means this value will be 10 plus the 3. So the 3 is not part of the clock arithmetic at all. So you get 13 for this. Any questions on the modular arithmetic? Okay. All right, so on to induction. So in last week you guys looked at some different proof techniques. There was a kind of a direct proof, or proof by contradiction, or proof by contrapositive. There are a couple of different proof techniques. And so this is another common proof technique, and it kind of goes in 3 steps. So we'll walk you through those steps. So the first thing you want to do is prove it true for the base case. So I often just label it the base case. So in other words, you want to prove it true for, n equals 1. Really, you can prove it for n equals whatever you want. N is usually the easiest. So if I plug 1 into n, on the left side, I'm only adding one number. You know, it goes 1 plus 2 plus all the way up to 1. But since I started at 1, I will end at 1. And then plugging in 1 on the other side, I get 1 times 1 plus 1 divided by 2, which is 1 times 2 over 2, which is 1. So I just proved it for the base case. Second step is to assume it's true. So assume your statement is true for some place and time. So at some point, we usually say at k. So assume it's true for n equals k. So that would mean we assume that 1 plus 2 plus ... up to k is equal to k times k plus 1 all over 2. So we're going to assume that's true, and then we want to show that it's true for k at the next step. So if we assume it's true for like 10, we want to show it's true, then it shows true for 11. So show true for n equal to k plus 1. So I'm just going to write out more of what that means in this example. So we want to show that 1 plus 2 plus all the way up to k plus 1. So I'm going to say plus k plus 1. Then I'm going to plug in k plus 1 on the other side. So I get k plus 1 times k plus 1, which is 2 over 2. So this is what I'm trying to show is true. And to do this, when you're trying to show an equality, you want to work with just one side. So I'm going to take just the left side, and I'm going to replace the 1 up through k with my assumption. I'm assuming that 1 plus all the way up to k is equal to this, so I'm just going to replace it. So I have k times k plus 1 over 2, and I'm going to add that. I have this k plus 1 still. And I want to work with this and show that I get this other side. So I'm going to add these two together, and to do that I'm going to get a common denominator. So I'm going to multiply this by 2 over 2, so it doesn't change anything. Now I can add them, so this have a common denominator. Notice the top pieces both have a k plus 1, so I can factor a k plus 1 out. And if I factor a k plus 1, so if I take a k plus 1 out of this side, I'm left with this k. And if I factor a k plus 1 out on this side, I'm left with the 2. And when you add fractions together, the common denominator stays. I get k plus 1 times k plus 2 equals 2, which is what I was trying to show, and thus I am done. So again, just to think about the proof by induction, you show the base case is true, typically n equals 1. You assume it's true for n equals k, so plug in k for n to show what your assumption is. And then you want to show it's true when n equals k plus 1. And then then you typically do algebra on that to get it to work out. All right, questions yet? Alright, so I have one more example of induction that is very similar to the very last homework question. Oh, Well, good. I'm glad we're touching on it. So what this means is, actually, let me just try to describe what this weird expression is before we try to prove it. So I'm just going to write it out differently. The big U means the union of all A sub I. So A sub I is some set. So all the A1, A2. So all the way up on. So this is really like A1 union A2 union all the way up to union AN. That's the long way of writing what's in parentheses here. We want to intersect that with B, and we want to show that's the same as, now I'm going to write this big union out. So it's A1 intersect B union A2 intersect B union all the way up to AN intersect B. So the common mistake on this type of question is, well, we have a theorem that just says we can distribute across the sets, but we don't exactly have that. We do have a theorem that says A union, oh, my writing is awful today, A union B intersect C is equal to A intersect C union A intersect, whoops, B intersect. B intersect C. And so this theorem, it looks like what we're trying to do, but the theorem we have only works for 3 sets. So in the green, I only have 3 sets there, but in the red, it's for an infinite number of sets. We don't know how many. So we want to apply this green rule. We need to get it to look like more like that first. So that's kind of our goal. All right, we'll see. I'll try not to run out of room. So as with induction, we're going to start with our base case. So want to show it's true for n equals 1. So I'm going to plug in 1 for n. That means my big union, this thing, is going to go from 1 to 1, which means that is just A1. So I have A1 intersect B. And on the right hand side, again, this big thing is going from 1 to 1, so it's just one set. And if I plug in 1 for I get A1 intersect B. Well, that is true, so there's our base case. We want to assume it's true for n equals k. So what that looks like is the union from 1 to k of AI intersect B is equal to the union I equals 1 to k of AI intersect B. So we're assuming that's true, and so somehow we want to use that in here. What we want to show true, now we want to show true for k plus 1. Alright, so when you put in k plus 1, you get the union I equals 1 to k plus 1 AI intersect B, and we want to show that is equal to I equals 1 to k plus 1 of AI intersect B. So as before, I'm going to work with one side. So let's just work with this left side and show that we can get to the right side. So if I have the union from 1 to k plus 1, that's the same as the union from 1 to k of AI union with a k plus 1. So I'm just pulling off one of those sets, and we're intersecting that with B. So now I have two sets. I have this union, and I have this a k plus 1. So now I'm going to apply the green theorem I have at the top, because I have just two sets. I'm going to distribute the intersection across. Alright, so this is equal to, losing some of my writing. This was B, and this is going to be equal to the union I equals 1 to k of my AIs, intersect that with B, and then union AK plus 1, intersect B. So and now I am going to run out of room. So now I can use my induction hypothesis and replace this piece, because I know that the union from 1 to k of AI intersect B is equal to this by my induction hypothesis. So now I get the union from 1 to k. I'm going to erase this top green one so I can write the final step up top. Alright, so again, using my induction hypothesis, replacing this piece, I get, this is the union of I equal 1 to k of AI intersect B, and now I'm going to just carry this piece up top. So I have union A k plus 1 intersect B. Well, now these two pieces are the same, so I can just tie them all together. This is the union of I equal 1 to k plus 1 of AI intersect B, which is down here, which is what I was trying to show. I feel like this is a mess. Hopefully that made some sort of sense. But that would be the end of the proof. And yours, the homework one, is very, very similar to this one.